This is 2011 FRQ number 5 in the non-calculator section. All right, at the beginning of 2010, a landfill contains 1,400 tons of solid waste. The increasing function, this is important, and by the way, the 1,400 is also important. W models the total amount of solid waste stored at a landfill. Planners estimate that W will satisfy the differential equation for the next 20 years. W is measured in tons and T is measured in years from the start of 2010. Use the line tangent to the graph of W at T equals 0 to approximate the amount of solid waste that the landfill contains at the end of the first 3 months of 2010, time T equals 1/4. So what this is saying is it's assuming that T equals 0 is 2010. That's your initial start. You start at 2010. And at the beginning, you have 1,400. So first thing you know for part A is that T equals 0, then W equals 1,400. All right. In order to write the tangent line, you need a derivative, which awesomely we have, right? We have dw dt. So dw dt, that is your slope. We want the slope for this function. It will give us the slope for writing this tangent line. So dw over dt equals 1/25. W is 1,400 minus 300. That gives me 1,100 over 25. Dividing that through, that gives me 44. So what is my tangent line? My tangent line is going to be y minus 1,400 equals 44, x minus 0. Clean this up, you get 44x plus 1,400. Okay, now you need to use this tangent line to approximate 3 months. 3 months of a year is 3 out of 12, which makes t equals 1/4. So t equals 1/4, y equals 44 times 1/4 plus 1,400. Gives me 11 plus 1,400, so 1,411 tons. So 3 months later, you have 1,411 tons. Okay, now find the second derivative in terms of W. Use the second derivative to determine whether your answer in part A is an under or an overestimate for the amount of solid waste that the landfill contains at time equals 1/4. First, let's find the second derivative. So if dw dt equals 1/25, w minus 300, okay, second derivative says, take the derivative, so this is a coefficient, 1/25. You need to find the derivative. Well, derivative of w is dw dt minus 300, that's a constant, so that's it, right? But what is dw dt? dw dt is this, so you just need to plug it back in again. I know it sounds a little convoluted, but this is the way it's working. It's implicit differentiation. So it's kind of like the implicit differentiation where we plug in the first and second derivative or the original function back into the derivative, okay? So that gives me 1/25 times 1/25, 1/625, w minus 300. Okay, so how do I know if this is going to be an over or underestimate? Well, then you need to figure out if you're concaving up or concaving down. In an earlier FRQ, we talked about this. If your second derivative says it's positive, it concaves up, then all the tangents are underestimates. If it concaves down, then all your tangents are overestimates. So you need to know the concavity of this. Well, the good thing about this is that you know that your function is always increasing, and you already start at 1,400. Which means your W is always going to be greater than 1,400, right? And no matter how high it goes, it's going to create a positive answer here. Multiply it by 1/625 is still going to be positive. So your second derivative is always positive. Hence, it concaves up, which means then we have an underestimate from part A, okay? So the concavity determines whether it's a over or underestimate. All right, last but not least, find the particular solution to a differential equation with the initial condition. All right, so this is another one of those where you gotta separate your variables. Okay, so part C says dw over dt equals 1/25, w minus 300. Okay, so this w minus 300 is one entity. It has to go on that side because it's w. So you divide it over and multiply dt over. So dw over w minus 300 equals 1/25 dt. Now you can take the antiderivative. So it's dw over w. This minus 300 is only important in terms of keeping it as a constant, but this is really dw over w, du over u, this is natural log. So this is natural log of W minus 300 equals 1 over 25 T plus C, right? So at this point, you have the initial condition of W is 0 equals 1400. Plug in 1400 for W, plug in 0 for T. So natural log of 1400 minus 300 equals 1 over 25 times 0 plus C. So natural log of 1100 equals C. All right, now what? Now let's plug it into our original equation right here, and we're trying to solve for W. So natural log of W minus 300 plus T over 25. I like to write less, so I write T over 25 plus natural log of 1100. Okay, so let's get rid of my natural log on the left side. Oops, not plus 2, we need pluses. Equal. All right, so get rid of the first natural log, e to both sides. So you get absolute value of W minus 300 equals e to the T over 25 plus natural log of 1100. All right, so this is a cool part. Natural log of 1100, if you do it like so, let's see if I have enough room to write this all out. So you have your e, this addition makes it come down. So e to T over 25 makes it multiplication e to natural log of 1100, which then makes this come down as a coefficient. So it's really 1100 e to T over 25 equals absolute value of W minus 300, right? So what does that mean? Well, whenever we have the absolute value, we create two equations. We're saying that W minus 300 is equal to 1100 e to T over 25, or W minus 300 equals negative 1100 e to T over 25, right? The absolute value says it can equal positive this or negative this. All right, so which one is it? Well, again, we need to use our initial condition again. The initial condition of 0, 1400 is going to be helpful. So let's plug in 0 and 1400. We get 1400 minus 300 equals 1100 e to the 0. So 1100 equals 1100. Yes, this one works. How about this? 1400 minus 300 equals negative 1100 e to the 0. So 1100 equals negative 1100. No. So this is my actual answer, W minus 300. So last but not least, let's move the 300 over. So your official equation is W equals 1100 e to the T over 25 plus 300. All right, and don't forget though, your problem did say something about for the next 20 years. So this is restricted. So your T is only good for 20 years. Okay, and that's it.